Welcome to The Deep Dive. If you've been following the world of engineering, well, you know we're on the cusp of something big, a revolution, really. Today, we are accelerating straight into the future of manufacturing, looking specifically at how artificial intelligence is driving a radical new approach to design. We're talking about potentially ditching traditional blueprints and, letting the machine invent the physical world around us.
That's exactly right. The manufacturing industry isn't just getting faster, it's getting fundamentally smarter. Our mission today is to take a really thorough look at AI-driven generative design, or GD as some call it. We're going to explore precisely how this tech moves beyond just basic optimization. It fundamentally changes the geometry of parts. And the result, designs with, well, unparalleled precision, efficiency, and cost effectiveness. It's about understanding that core mechanism, how AI can design something lighter, stronger, and maybe cheaper than any human engineer could easily conceive.
And that leads us right to the hook, doesn't it? The core distinction that makes this tech a genuine game changer. Generative design uses machine learning, sophisticated computational algorithms to create optimized designs. And the key word there is create. The AI doesn't just tweak an existing human design, using old CAD models. It often starts from scratch, from a blank slate, and generates completely novel shapes. Complex, sometimes organic-looking structures.
Yeah, things you wouldn't expect.
Exactly. Shapes that are often impossible, or let's be honest, far too time-consuming for a human engineer to develop manually. It's almost like a design partner that thinks entirely outside the box, often leveraging physics in really counterintuitive ways.
That's a good way to put it.
So let's dive into the nuts and bolts for you, the listener. What exactly is the process here? What input are we actually giving this AI?
Well, the process fundamentally inverts the traditional engineering workflow.
Right.
I mean, historically, a human designer sketches a shape.
Right.
And then they use analysis software, maybe something like finite element analysis, FEA, to check if that shape will hold up. Generative design flips that completely. The engineer provides the performance constraints, the rules, and the AI designs the shape to meet those rules.
Okay.
The mechanism itself is fascinating. The engineer sets the rules, and the AI starts to sort of grow the solution.
Yeah.
And we're talking about very specific, predefined parameters here. These aren't just vague goals like make it strong.
No.
No. It includes necessary material properties, the environmental constraints, things like specific heat loads, expected stress cycles, and really critically, the exact load paths, where forces will be applied and where the part needs to anchor.
Okay. So instead of me designing a basic bracket and then asking the computer, hey, is this strong enough? We're telling the AI, look, I need a connection between point A and point B. It has to handle, say, 10,000 pounds of force, but I only want to use the absolute minimum amount of titanium possible.
Exactly that. Yeah. Nailed it. And it's not just a simple linear calculation either. The AI system uses advanced techniques, often based on things like evolutionary algorithms or maybe reinforcement learning, to run thousands, sometimes millions, of computational simulations. It generates this huge array of design alternatives.
Wow.
And it virtually stress tests every single one of those options against all the criteria you set: deflection limits, vibration damping, whatever it might be. And this whole iterative process leads directly to what you see in the final output. Those incredibly complex, sometimes unsettlingly organic geometries.
They really do look like bone structures sometimes, or tree roots.
That's right. Because the AI is essentially optimizing material only for the precise locations where those load paths demand strength.
Yeah.
It hollows out every single unnecessary bit of material. This is often referred to as topology optimization. And it's how this technology fundamentally separates itself from older, more human-led design methods.
I find it absolutely fascinating that the machine's answer to efficiency often looks so natural, so organic. It's almost like it's mimicking evolution to get maximum utility.
That analogy is pretty much perfect, actually.
Yeah.
Because evolution doesn't design a square beam just because it's easy to mill.
Right.
It designs what is needed efficiently. And because the AI can test, 1,000 different complex iterations in the time a human might sketch 3 simple ones, it arrives at solutions that are often non-intuitive to us, but vastly more efficient from a physics perspective.
Okay, that's the mechanism, how it works. Now, let's talk benefits, the balance sheet, if you will. What are the concrete, measurable benefits manufacturers are actually seeing right now? Where's the ROI when they jump into generative design? We identified 4 key areas, didn't we? And we need to go a bit deeper than just, it saves money.
Definitely. The first benefit, and this is the one that really sells the concept, especially in sectors like aerospace, is improved performance via weight reduction. And look, we aren't talking about tiny marginal gains here. We've seen examples where optimizing just a single engine component, like a large structural bracket using GD, resulted in weight reductions of 40%, even 50%.
10, that's huge.
It's massive.
Yeah.
And this directly enhances strength and durability too, because the material is placed optimally. It ensures superior quality that's been rigorously tested in a digital environment, mimicking real-world conditions before you even make the first physical part.
And that significant weight saving, that feeds directly into the second massive benefit, doesn't it? Cost reduction, which seems to have two angles. First, obviously, minimizing material usage means less raw material to buy. That's a huge saving, especially with expensive stuff like specialty alloys.
Absolutely.
Second, it sounds like it eliminates geometric inefficiencies, things that lead to unnecessary weight or maybe needing complex multi-part assemblies that the AI can just combine.
Precisely. When you design using AI, the result is lighter, stronger parts needing significantly less raw material. That cuts waste, lowers the overall bill of materials. Big win. But the secondary cost reduction is just as critical. Streamlining the design process itself. Think about it. Engineers are freed from tedious manual iteration and complex analysis.
Yeah, that must save a lot of time.
It reduces the time and resources spent in that R&D stage significantly, which naturally leads us straight to the third major benefit: faster time to market.
I mean, if a traditional product development cycle takes, say, 12 months, and you can potentially cut out 2 months of design iteration because the AI handles the complex calculations and simulations in days, not weeks, you gain a massive competitive edge, right? Companies can accelerate their iteration cycles, get products out the door quicker than their rivals.
Exactly. And finally, the fourth benefit, and this one is becoming increasingly important, to consumers, to shareholders, it's sustainability.
Ah, right, the green angle.
Yeah. When you connect those lightweight designs to that substantial reduction in material waste, using less of those often expensive and sometimes polluting raw materials, generative design becomes a huge win for the environment. Yeah. It's kind of a dual benefit, really. Good for the bottom line, good for the planet. You're just using way less stuff to build the same functional thing.
Okay, this is where it gets really interesting for me, connecting this powerful theory to the real world. Where is the rubber hitting the lighter AI-designed road right now? What are some concrete examples?
Well, as we touched on, probably the most critical adoption, certainly the earliest, has been in aerospace. For commercial aircraft, I mean, even a tiny reduction in weight translates to immense fuel savings over the life of that plane. Millions of dollars.
Incredible.
So manufacturers aren't just optimizing simple parts. They're using GD for critical engine components, complex fluid channels like fuel lines, large structural elements like ribs and spars. The focus is always on maximizing strength while stripping out every single superfluous gram of mass.
Okay, so aerospace is leading. Moving closer to the ground, we're seeing massive use in the automotive sector too, right? Which is obviously going through its own dramatic transition at the moment.
Absolutely.
Whether it's traditional gasoline engines or EVs, weight is the enemy. It hurts fuel economy, it kills battery range, it affects performance. So companies are using generative design to shave ounces, maybe pounds, off crucial safety components, battery housings, suspension parts, all sorts. Lighter parts mean better fuel efficiency or maximized battery range without compromising safety. That's key.
Safety is paramount, yes.
Yeah.
And the third major area we're seeing huge strides in is the medical industry, particularly where customization is absolutely non-negotiable. Generative design is driving the creation of custom products, specifically AI-generated prosthetics and implants. Think hip replacements, knee joints, spinal implants.
Personalized parts.
Exactly. Because the AI can optimize the geometry based on an individual patient's unique, complex anatomy, maybe their specific gait, the expected loads. The result is just a much better fit. Faster recovery times, improved functionality for the patient. It's almost the ultimate personalization of manufacturing, driven by AI.
So the AI is basically designing potentially better hips and better braces than human anatomy has managed so far. That's a high bar.
It is a high bar, and it's achieved through a level of precision and optimization that, frankly, no human designer could realistically manage manually.
Okay. A technology this powerful, creating these intricate, sometimes lattice-like structures, it must have some fundamental hurdles, right? Some challenges. What should manufacturers be aware of as they consider moving into generative design? Because like you said, if the AI creates a shape that looks like a piece of coral reef, well, we can't exactly machine that on a standard 5-axis mill, can we?
That's a brilliant way to frame the complexity. And you've absolutely hit the nail on the head regarding that crucial link between design freedom and production reality. While the potential is immense, Yes, there are real obstacles, particularly for manufacturers maybe operating with more, let's say, legacy equipment or processes. The first significant hurdle is definitely integration complexity and manufacturing constraints. You touched on it. These generative designs often lean very heavily on additive manufacturing, 3D printing, basically.
Right, because you need to build those complex internal structures layer by layer.
Exactly. Traditional methods like casting or machining often just can't create those organic internal lattice structures the AI comes up with. So integrating generative design often means a company has to invest not just in the software, but potentially in an entirely new, often expensive, additive production line. And that's definitely not a simple plug-and-play solution.
And complexity like that often leads directly to cost, which I imagine brings us to the second major issue.
You got it. The second challenge is the high upfront costs and the need for skilled personnel. The initial investment in the software itself, the sheer computational power needed because running those thousands or millions of simulations isn't cheap, and then the necessary 3D printing equipment. It's significant. But perhaps the greater long-term cost or challenge is personnel. You need skilled engineers who are trained not just in traditional CAD, but in operating these complex AI tools, interpreting the output, validating it.
Knowing how to set the right constraints in the first place, I suppose.
Precisely. That requirement for specialized talent can create a pretty significant barrier, especially for smaller manufacturers who might not have the resources for that kind of upskilling or hiring.
Okay, cost and skills. And finally, we're talking about an AI creating a unique, novel design, something that's never existed before. That design itself is inherently valuable. Who actually owns that geometry? That seems like a tricky one. That is the third major obstacle, and it's a big one: intellectual property, IP. The IP concerns around AI-generated designs are significant and still actively developing in legal circles. It's murky territory. How so?
Well, think about it. Is the IP owned by the engineer who skillfully set the constraints and parameters? Is it owned by the company that licensed the generative design software? Or maybe it's owned by the software company that created the underlying algorithm that did the generating.
Yeah, I see the problem.
That lack of clarity around establishing ownership, the legal parameters, it's genuinely slowing down adoption in some risk-averse industries.
It forces manufacturers to move cautiously, doesn't it? Because they can't afford to invest heavily in developing a unique, optimized product design, only to have it potentially tied up in legal disputes for years. Precisely. So it's really important that we frame these challenges not as, insurmountable roadblocks that stop progress entirely. They're necessary considerations. Manufacturers need a phased, thoughtful approach to adoption, one that accounts for these technical, financial, and, yes, legal complexities along the way. That's a really critical distinction. So to sort of summarize the main takeaway here, AI-driven generative design is clearly poised to transform the entire manufacturing landscape. There's no doubt about that.
It's optimizing performance and cost, often simultaneously, by creating fundamentally new geometries. It seems to be leading us into a new era defined by, well, efficiency and sustainability. Absolutely. If we connect this to the bigger picture, this technology is genuinely moving us away from relying purely on human intuition and design towards true physics-based optimization. It really does feel like the definitive future of manufacturing design. And yes, while integration hurdles and upfront costs present real immediate challenges, the long-term benefits, the ability to create parts that are stronger, lighter, maybe use 50% less material, they're just undeniable. Manufacturers who adopt this technology now, even with the challenges, are gaining a crucial, long-lasting competitive advantage.
Absolutely. Seems manufacturers who embrace this are positioning themselves for success, not just competitively in terms of speed and cost, but also in an increasingly environmentally conscious market. Efficiency and material reduction are huge selling points now. It really makes you wonder, doesn't it? If the AI can take a relatively simple component like a bracket and make it 40% lighter and just as strong, what seemingly intractable structural problems, maybe in civil engineering or energy infrastructure or even urban planning? What could you, the listener, imagine solving if you had an AI designer working 204/7 on pure optimization? Something to think about.